Hey class. So I wanted to spend today discussing a little bit about numerical methods of integration. So a way to program an integral, the concept of a definite integral, or as we'll see in a little bit, the integral of a dynamic system. And so we'll start with that, and then we'll jump to AVL trees. And that will be the entirety of the class. Okay, so if you look here at the top, we have the fundamental theorem of calculus. I believe this is the second fundamental theorem of calculus. So essentially, the fundamental theorem says that there's this very tight relationship, this intrinsic relationship between the rate of change and the rate of change for a given function, so little f, rate of change, for a given function, big F, where if you go in the other direction, then you sample that rate of change, and then you make the samples closer and closer together, and then you integrate against it. You find the area, or you construct some area. Then that original function, so the one for which this is the rate of change, it can be used or it is the solution to the definite integral here, right? So it doesn't really make any sense why we're doing that necessarily whenever you first learn it in calculus. You learn that it's a theorem, you may even learn the proof for it, but it's not exactly intuitive why we're doing that, what exactly is happening there. And so I wanted to spend a little bit of time discussing that. It's like a concept that I believe is traditionally not taught until a little bit later on, but I do believe that at this point you all have the groundwork already laid to kind of understand what's going on, and if not, you can essentially construct it from algebra. I mean, Newton just kind of went crazy with algebra, and he invented calculus. So. And I don't remember exactly how old he was when he did it, but he was pretty young. I think he was still a teenager whenever he did it. Calculus is in essence, in that sense, an extension of algebra. So, quick review: rates of change, right, are just you have it's a computing slope. So, whenever you first learn the slope of a line, you have some point and then some other point, and then you have between them you will have traveled some distance in the x direction, and some distance in the y direction. So that's this way. And if you find that ratio, so if you compute the actual distance between these 2 points, then you get an answer. So for every number of units moved horizontally, you move some number of units vertically. And so this is the slope of the line. And so, for a while after this was originally discovered, and I imagine that it was discovered pretty early on. Basically, as soon as they started using Cartesian graphs, you would figure out how to compute the slope of a line. They really only used it for computing lines. So if it was like something of the form y equals mx plus b, then you can use this to compute that. And then Newton and around the same time Leibniz realized, well, you can use approximations. So even if the line is curvy, then you still get a bunch of points if you get close enough together where from here to here it looks like it's moving in a straight line. And then from there to there it's the same phenomena. It looks like a straight line. And so on and so forth. So that formula applies. You get something regardless of how curvy your plot is. If you're sampling close enough together, you get these changes that are moving in a straight line. So we have slope m1, slope m2, slope m3, and slope m4, where yeah, sure, the rise over run is a little different when measured at each one of these points, or between any pair of these points, any pair of these adjacent points. But it's consistent. You can use it to predict a future value and to get a pretty close approximation. And in fact, the claim that Newton made and kind of his contribution was with limits. Well, yeah, he made several contributions, but one of the breakthroughs was really in considering these limits. It's like, well, if you just let it get as close as you want, so then your error or the error in those consecutive measurements gets as small as you want. And so he kind of played around with it. He just explored, like, okay, well, what does this mean? And so here, if we imagine that this really curvy one is some value f of t, right? That should really be f of t. Then, oh, no. Never mind. So it should be little f of t. Then, right. So he played around with it, and he discovered each of these different slopes. And so, if you were given any starting point, then some starting point f of ti, then you could use the slope just like you would if you were computing some future point with something of the form y equals mx plus b. So you have x naught, and then you can compute some future value xi or yi. So you have y naught or y0 associated to some initial point. And then if you have the slope, then you can use your knowledge of that one point and the slope to compute some future value. So if you go x units further, then the slope times x is going to give you how it moves from that first point, right? So right? So if we're starting at this point and then we move here, well, and if we know, so for instance, if instead of x we have t, and so we're measuring something in units of time, and we have a stopwatch, then we can compute the number of seconds, and we want to know, okay, well, how did this thing move, in whatever way it was going to? Well, if you have these approximations, then you have your difference in time, your delta t, or your dt, which is the notation that we use once it gets infinitesimally small. So you have your dt here, and you can use that to compute your dy or your df, the derivative. So so that change, the change in motion in the y direction can be computed from a known slope times a measured change in time. Okay, well, whenever we're programming, we control the units of time. We can say how often we want something sampled, right? So this dt is not just some notational thing. Like, we're actually multiplying times some arbitrarily small change in time to get some estimate. And then this, has a geometric meaning. So whenever we're sampling this, the integral sign, the fact that it looks like an S isn't a coincidence. It's it's meant to stand for sum. So it is a special notation of this, a summation, a series of additions where you've moved to a limit. So it's just a shorthand for this, right? This infinite sum. And so this, if you're going to use the Riemann sums, then you're using rectangles. So you have a width, right, or a base if you prefer, and you have a height here. And the first term in your summation is the area of this rectangle, so it's your height, f measured at that first point, times your change in t. And then you have your second measurement, which is just another rectangle. And you can already see this area that I've shaded in is an air term. So the fact that we're doing this using rectangles is already highlighting that if we get too far apart and it's a really curvy line, that we're going to be introducing all sorts of air. So there's a couple of things we can do to solve that, or to reduce that air. So one of the things that we can do is to move the points closer and closer together, and then the air will get smaller and smaller, but it'll happen linearly. So we won't see that much improvement until we really scale up the number of points. Another thing we could do is to use an average of these 2 points, so that our rectangle looks like this, and essentially essentially about half of our rectangle is overestimating the area, and about half of it is underestimating it. So this part is the underestimation, and this part that hangs outside of the curve is the overestimation. And when you say that, it's like, well, what kind of approximation does that have? Well, so I was using a triangle to approximate the air, and so that triangle is actually exactly the area using this method. So that's called the Trapezoid Rule. So you could say you're taking the average of those 2 points, and you're using a rectangle where the air is on. You're both undercutting and overcutting it, but really, like, you're instead of just a rectangle, you're drawing a trapezoid where you have the rectangle and then you include some additional triangle of area on top of it. And so the trapezoid method is a little bit more accurate. And then once the groundwork was laid for calculus, and you realized that you could compute the area under this curve, there were several other methods that were taken into account, and one of them was Simpson's rule, which if I move quickly enough, we'll get to discuss that. So okay, so that's quick review on calculus and using area of the curve and slopes and so forth, and that relationship between this function which represents the area under the curve, and then the slopes on top of it, or the slopes of this curve, which is some changing value. Okay, so we have that relationship given to us by the fundamental theorem of calculus, but for numerical integration, we're going to say, okay, well, we don't know what this value f is. Like in fact, we have some understanding of what the function that we're sampling is, in certain really complicated scenarios, and we will get to that. So we have some idea of what our sampling function is, but it doesn't have an integral in the analytical sense. So there's not something that I can say, y equals, x squared or something, and I'm integrating that. It's, when it has this velocity and, something else, and, this velocity and this acceleration and this amount of drag, and there's not some external force, or sometimes there is this external force, or there's this headwind that happens when you get to this point, and so you have to take that into account given your velocity whenever you get there. It's something that is more modeled after what we would experience whenever we're moving through the world. We don't move at velocity t squared or whatever. We react to whatever is presented to us, and so those more complicated systems where your position is a function of time, and there is a velocity and acceleration component, but it kind of depends on when you saw the red light, and your car starts decelerating or whatever because you have reacted to the system, or in the case of the motion of planets and bodies in space or whatever, it depends not just on the time or whatever, but there are these external forces that you have to take into account, and so essentially this concept, this numerical concept, goes from this precursor to this analytical solution to the only game in town. It's the only way to approach these problems where you have absolutely no hope of finding some value, capital F, and the integral, the concept of some small change in time adjusting your position in this extremely complex system is the only way to represent it. And so numerical integration, while it is great for the lazy developer who doesn't want to remember too much about calculus and just wants to sample and have his computer compute rectangles or whatever, it becomes the way, right, for this dynamical system. So I wanted to introduce the concept to you, and time permitting, we will explore it a little further later on. So there's 3 examples in increasing order of difficulty. Okay, so this first one, right, we can compute the integral, right? So we have this constant function f of t equals 1, and we want to compute the area under the curve. Okay, so it's 1 unit in height and b minus a units in width. So it's that rectangle right there, the area under that curve between this point and this point. So analytically, we have our solution. We have our integral from a to b of f1 of t dt. And the integral of a constant is going to be that constant times the variable of integration, right? So d. And then we evaluate it from a to b. So t evaluated from a to b is b minus a. Okay, so we have that. And then the 1 is just kind of lost in there. If we, this is really the constant, 1 times t, so it would be the constant times b minus a. Right? So that's our analytical solution. So let's take a look at programming that, at numerically evaluating that. Okay. Okay. So I put the sampling function there, so little f of t, and we're going to use that to compute our integral. And this notation should look a little familiar if you've been doing the LaTeX work. And so we have some constant times dt, we're integrating some constant. And so the area under that curve we would expect to be that constant times b minus a. And we just went through the work for that. Okay, so let's set up the problem. So we have some initial point, 0, or we can move it down the line and make it 5. And then we have some other point, we'll say 10. Right? So that's the last point of evaluation. We have a number of samples that we're going to take. We'll say 100. And then we can compute dt, so our step size as we're evaluating these rectangles to compute area under the curve. And that's going to be b minus a divided by the number of samples. So our step size is that. Okay. So our sum, our integral, our numerical integral, is initialized to 0. And then the constant that we specified here, right, f of t is just a constant value, is here, so that we can play around with it. So we'll say that it's 1. And then we create our function f of t, and it's just a constant, right? So this is exactly what we specified. Some function which takes t as a parameter returns the constant value c. So this looks pretty similar to the one that we specified. Okay, so now whenever you see a summation in mathematical notation, it's going to be a for loop, right? So you have some initial value in the summation. So n equals 0. N less than k, right? Which here we've called the number of samples. And then we increment it at every step. Okay, so then we tally our sum with the rectangle generated by f of t, where t is our starting x value, or our starting t value, plus the sample number that we're on times our step size. So if we were taking 5 samples, then for this first value t would be 5. The second value, t would be 6. The third value, 7, 8, and then 9. And we wouldn't draw a rectangle extending beyond 10 because 10 is our stopping point. Right? So we've computed our step size, and we have the number of samples already measured out. And so that's what we're doing here. Right? So that's what this is. It's just computing the appropriate value of t. Right? And then dt, just like in the integral, right? So f of t times dt. So f of t times dt. Right? And that's our sum, right? We said the integral was just a special notation for a summation. Okay. So then let's write that out. We'll see whatever our value was. Okay, so this, the fact that it's not exactly 5, which is what we would expect, right? So b minus a, b is 5, times our constant, which is 1. So we would expect that to be 5. 5 times 1 is 5. So why are we getting 4.999? So this is a limitation of floating point arithmetic, and it's why we use tolerances or neighborhoods around some value that we're expecting, because what we would get when we compute it by hand is not necessarily what we would get whenever we compute it using floating point arithmetic. So here, let's change this to power of 2 and see if we get a different result. We'll say 4. Right. Okay, so computers work much better with powers of 2 than powers of 10. So we're familiar with powers of 10, but the computer is going to more precisely represent division by some power of 2 than otherwise. Okay, but this is an important lesson that we should expect when dealing with floating point arithmetic or with fractions to get some results like this. So if we're testing to see whether or not the value equals what we expect it to, we should allow for some tolerance, some amount of error to kick in. So let's make this into a test case, right? So let's say we're developing some numerical integrator, and we would have the value that we expect. So this is what we computed that the integral should be, right? And then we have the actual result, which is the sum that we computed using our summation. And then we have some tolerance that we say, well, if it's in the neighborhood, then it was right. It's just some limitation. And we can make the tolerance as small as we want. So in this case, we're going to make it something like 1 will allow for an error 1 part in like every 8,000 or something like that. Okay, 8192, something like that. 1 in 8,192 parts. Okay, so now we have our test, right? So if it's in the neighborhood, if the absolute value of the difference between the expected result and the actual result is less than our tolerance for error, or less than or equal to, in case we get it, exactly right or whatever. So if we bump our tolerance down to 0, then we want this test to still pass. Then we just put out that the test passed. Otherwise, we write some error. And then we indicate what the error was. Okay, our test passed, so we succeeded on our first integral. Excellent. Okay, so now we move on to the second integral. So the second integral is pretty simple. It's just a line. It's the the canonical line, f of t, or f2 of t, equals t. So then the integral of our second function, f2 of t, dt from a to b, is going to be 1/2 t squared evaluated from a to b. So we plug in b, and we subtract a from that, and we get 1/2 times, in parentheses, b squared minus a squared. Or if we separate it, we get 1/2 b minus a times b plus a. So what is it we just did here? Well, okay, so we have some point here, right? And our input value was a, and because our function, the output is always the same as the input, then we know that this point is AA. And we know that this point is BB. And then we've gone through the trouble of creating this integral so we can compute the area under this curve from evaluated from this point to this point. So we want to know the area of this trapezoid. Okay, so the trapezoid, the area of a trapezoid, is okay, so it's what we were just saying, where it's the average of these 2 points times the base, or if in the case where we start, where right, where we're starting from the origin, then we can see that it follows the triangle formula, where we have the base times the height, and so we make a note of that. Okay, so what we would expect is if we have a trapezoid where this is 2, 2, and this is 3, 3, then we would expect the area to be right, and so again, that would also be a triangle sitting on top of a rectangle. So we would have b minus a times height a for the rectangle. Okay, and then we would add that to to this triangle, right? So 1/2 based on height. Okay, so that's another way to look at it. But anyway, so we've computed the area analytically. We have our test, and then we want to see if we can get an approximation of this using a numerical integrator. So let's write that. And again, I like to be pretty liberal with my comments, just to give myself as much of a hint of what I was trying to do as possible. And then if you ever go back and evaluate your notes later, it can be helpful. Okay, so we've already declared these values above. We'll just reuse the variables. So we have some region, right, and some number of samples. And what did we use before? Something 2 to the 4 samples. All right, sure, we'll give that a shot. And so again, our step size is the width of our range divided by the number of samples we're going to take. So we're taking this many steps, so it would make sense that our step size would be this divided by our number of steps. Okay. So then again, we reset our integral, sum equals 0. This time we're not defining that. We're redefining f. So f is again a function of t, and this time it returns t. Okay. So now again, an integral is just a summation. And then again, we sample. The expected value, which was our analytical solution. The actual value, which was our numerically computed solution, and then our error tolerance. And again, we're going to pick something like 1 part in 8192. And then we're going to see if our expected value, if the absolute value of the difference between our expected and actual value was in the neighborhood of our tolerance, or was within tolerance of the expected value. And if so, we're going to give a friendly message saying that our test passed. Otherwise, we're going to write to the error stream that our test failed, and then say what we expected and what we got. And typically we would actually give a name to the test. So we've been numbering our functions. So we'll say F1, F1. Although we don't need to do that. We're already labeling them in the comments, right? So we'll say example 1, test failed. Example 2, test failed. Okay. So let's run it and see what we got. And it failed. So let's take a look at why. Okay, so our value was just a little bit off. Let's see if we increase the number of samples, if we get better results. So we're going to go from 32, or sorry, from 16 to 128. And we see that we're getting a little bit closer. Right? So let's double it again. So now we're going to run 65,000 samples. And we're getting closer. So let's really ramp it up. And we'll say, okay, well, I want, give me like 1 million samples. And it passed. Okay, so what we see there is that is exactly what we'd expected. So the accuracy of our sum increases as the number of our points, or as the number of our samples gets larger, or alternatively, as the samples that we take are at increasingly closer and closer points. And so for the original one, when we had this simple area where it was just a constant, we were just measuring the area under a constant slope, it was linear, and it really didn't take a lot of samples to get the accuracy that we were looking for. We just had to use some power of 2 to get what we wanted. But for this one, where it was nonlinear, because the area is changing very dramatically based on how far up the values of t we go, then we needed more and more samples. And so we could have increased our accuracy using the trapezoid method, which would have looked like this. Let's see. So let's make sure that still works. Okay, so that's correct. So what happens if we go back to 16 samples? And it's perfect. So we were able to satisfy the exact same thing using the trapezoid method. So we find that if we don't use rectangles, if we don't use the simplest approximation, then we can get much better results in way fewer samples. And in fact, because we're measuring the area under this sloped line, the trapezoid method is exactly what we're looking for. So there would actually be some error to wrangle with if we were doing it under a curved line, computing the area under a curved line. But already we can see that something other than rectangles can function for us. And so depending on the method of integration that you use, you get a different error component based on just whenever you cut it off, whenever you limit the number of samples. And so for Riemann, the error is linear, and I believe for the trapezoid method, the error is going to be on the order of h squared or dt squared or whatever. And so you think, well, okay, whenever we compute runtime, something that's n squared is worse than something that's on the order of n or n log n. So why is it better now that we have this error term? Well, whenever you're increasing whatever is inside that big O notation, then higher degree or higher order is bad. But whenever you're getting closer to zero, when you're approaching zero, then higher order means that the error disappears faster. So it's actually good in that context. So whenever you're taking samples in the context of integration, you actually want higher degree of vanishing error term. Okay, so we've introduced that. So what is our last integral? Okay, perfect. So the last integral is actually going to be something that's a little more complex. You might encounter it in differential equations, in ordinary differential equations. You might see it, but it would be an example of constructing an ODE, and it wouldn't necessarily you wouldn't necessarily be required to solve it. Okay, so now we have a generic derivative, right? So we have some function f, which is the derivative of some other function, right? So here f3 takes as parameters t, so time as before, and y, where y is now a vector. And we'll get to that. Okay, and so the output of this is a rate of change on that initial vector, or on the vector that's passed in. And so this is what I was talking about with a dynamic system. Right? So the graduate school interpretation of this differential equation is that, yeah, this integral is going to have the same form of a solution as everything else. You have some integral evaluated from a to b, right, of some function times step size, and that equals who knows? It doesn't really equal anything, actually. So it's not always going to have some clean solution of this form, like we're encouraged to consume in the fundamental theorem of calculus, and like we've been dealing with over here. We have a dynamic system which evolves over time, and so you can compute position, and in this case we're going to deal with a ballistics problem here. So you can compute position, and it definitely evolves with respect to time, but how it evolves and where it goes is it's more than a nightmare to compute. It's actually impossible to compute analytically. You have to solve it by walking the path. You have to see, okay, well, if I just follow this thing and I measure, how it's moving at each point, and I follow these rules to get my next point, then I can see where it ends up. And then, as before, if we increase the number of samples and we decrease the step size, then we get increasing accuracy here. So here, the vector that we're going to use is, we're calling it y, or we could call it x. In fact, I think I'm going to use x in the example that we have. So we have some vector, it doesn't matter, and then just like an array. So at this point, it's not x, y, and z, it's x, y, and then whatever else we feel like sticking in there, right? So we have some value x, some value y, so position x and y, and then a value theta, which is it's ballistic, so we're dealing with Okay, so we're dealing with, like you can think of a cannonball if you want, or something like that, and it has some initial position, and we're going to launch it, and so we're going to launch it at some angle to the horizon, right? So, and then we're going to have some initial velocity, or actually. We're going to have some speed, not velocity. Speed is what we care about here. Okay, so it's going to move like that. Well, that's just a ballistics problem, right? Like we can compute that. So we know that the acceleration from Earth's gravity is 9.81 meters per second squared down, back towards the Earth. And so we can compute x just based on how long it takes for the ball to get to height y equals 0 again, right? So x is just the whatever that initial velocity was. So we have the speed is. So the x velocity is the overall speed times cosine theta, where theta is the launch angle, right? And that tells us how much of the speed component was in the x direction. And so if we compute t from just waiting for it to hit the Earth again, then we can use this initial x velocity times however long it took to come back to Earth to compute a straightforward solution. So why are we dealing with this with numerical integration? Okay, well, so let's say that the actual trajectory is or the actual motion of the ball is a little more difficult than that. So we know that ballistics problems or everything, I mean cook time itself, is different at higher altitude, and that's a result of lower air pressure, and so everything. It takes different amounts of time for things to boil. It takes a different amount of times for things to react. There's less air for stuff to happen. And so, in baseball, the Rockies and their home field tend to allow more home runs than everywhere else. And it's because there's less wind to resist the ball. And so that's one component. And then also the shape of the object traveling through the air is also going to make a difference. Something like a dart is designed to pass through the air a little more easily than something the shape of a baseball or a frying pan or a parachute, right? So the shape and in particular the resistance that shape has to the air is actually going to make quite a bit of difference. And so that term is going to be the drag term. So we're going to have a bunch of additional concepts to introduce. We're going to have gravitational acceleration, which we were using before, but now we're going to have a drag coefficient, which depends on the shape. We're going to have an air density, which is what we were discussing. It's different at sea level from in the Rockies. The cross-sectional area that's exposed to the air density, so exactly how big of a surface area is interacting with the air. The mass of the object, and then the rest of the problem follows from there, right? So we're going to see how this, how we can use numerical integration to actually come up with a solution for, where this cannon hit, let's build out the problem and we'll go from there. And I'm beginning to be a little skeptical that we're going to have time for ABL trees, but who knows? We'll see, right? So, okay. So let's get to this problem. Okay, so now we have example 3. Okay, so we have our vector, right? And I'm going to use LaTeX notation, just because it's as easy to read as any other format for me, and they're my notes, so it's whatever I'm comfortable with. Okay. Yeah. Okay, sure. Okay, so the first value is the value of x at that particular time. The second entry in our vector is the value of y at that particular time. The third entry is the angle with the horizon at that particular time. And the fourth value is the speed, right? Or the absolute value of the velocity. Okay. And then the derivative of this is going to be done component-wise. No, sorry, this is actually omega of t. Well, whatever. So angular velocity is the change of theta with respect to time, right? But whatever, it's the radial velocity or the angular velocity at that point. And then this actually is dependent on time. Okay. Well, with respect to t, obviously. Okay. We'll go ahead and put dt. And as you can see, there's several ways to note a derivative. It's whatever is appropriate at the given moment. Okay, so it would be helpful for our notes if we put this in terms of those values that we were representing up here. So how do we compute this, right? Okay, so the x velocity is going to be the speed times the cosine of the angle with the horizon. Right? So it's the same way that we used to compute the initial velocity, but now we're just computing it differently, and it changes with time. The y velocity is the same thing, but with sine. Our radial velocity is going to be computed from the gravitational acceleration divided by our speed times the cosine of theta at that point in time. And then our speed is going to account for the drag of the object, and we'll give that definition in a little bit, divided by the mass minus the gravitational acceleration times the sine of our angle. Okay, so I mean, does it get any easier? Okay, and then our integral, right? So the way that we would note it is that we have an integral evaluated from some initial time to some final time, and then we're sampling our function, our differential here. This is our sampling function with step size dt. And it's the integral from a to b of this, right? Just algebraic substitution dt, right? So we replace this with its equivalent value, and then we have a dt at the end, and so we have the dt there. Okay, and so unlike before, where we were able to analyze it and come up with a solution, we have no idea what this is. So the numerical solution is actually going to be our correct one. And if we had real-world values for these, then we could use that. But what we just have to kind of do this through trial and error. And then once we have an algorithm that's correct, we would actually use that to measure the other values. So if the air density was known and cross-sectional area is measurable, then we could compute the drag coefficient for a given object by measuring with a given launch angle and so forth. If we run it over and over again and then we account for statistical variances, then we could actually compute the drag coefficient for it and so forth. So that's where we get those empirical values that we're going to use. Okay, so we're going to use some constants for this. And whenever I do this, I always include the units. Okay, and then initial speed is the last one that we'll initialize, and that's meters per second. Okay, so we're almost done setting up the problem. We need to choose some launch angle, and so we're going to optimize for distance, and I'll leave it to you in physics or whatever to recognize that the maximal launch angle happens whenever it's 45 degrees or pi over 4 radians. And so essentially whenever you increase the angle up from 0, you get a further and further distance, and then once you start aiming above 45 degrees or pi over 4 radians, you start getting shorter and shorter distance. And intuitively, if you have a launch angle that's 0, then you're shooting it even with the horizon, and if it's truly at ground level, then it's just going to hit the ground and not go anywhere, or it would roll. But if you're counting from where it first lands, then that would be it. And then you would hit that same point, so 0 distance, if you had the cannon pointed straight up. So it would go straight up and then come back down, if there was no wind to blow it. And then you know that there are other distances in the direction that you would point the cannon, right? And so those are all of the other angles. And so you could imagine, that approaching from 0 going up, or from 90 degrees or pi over 2 and then going down, that you could continue to hit the same points. And so every point between that maximum distance and the minimum distance, which is 0, is going to have 2 solutions. So the one below 45 degrees, or pi over 4 radians, and the one between 45 degrees and 90 degrees, or between pi over 4 and pi over 2 radians. And so that maximal value is where those 2 points, the high solution and the low solution, meet. And so it increases and then it decreases coming back. So we'll just start at the maximum and see how far we get. Okay, and so our vector is just an array, or in C++, it's actually called a vector. So we're initializing our vector x of t with position at the origin. Okay, so again, we initialize our time component, and we'll just go from 0 to, we'll say 1. We'll let it fly for 1 second and then see where it's at. The number of samples should be some power of 2, as we've learned. So we'll pick a decent distance. So let's say that it's 256 samples, so a decent number of steps. Okay, so again, we compute dt, and it's the width of our journey divided by the number of steps, and that tells us how far each step needs to be to complete the journey. We again define our function f, but this time it's a function of t and a vector, and it's going to modify that vector. Okay, so we extract the variables that we need. So x of 2, or so 0, 1, 2 is our, at this point it's not our launch angle, it's our angle with respect to the horizon. So we call it theta. And then our speed. And now we get introduced to drag. So drag is a force. It's a retarding force on the object traveling through space. And so force is measured in newtons, and newtons are mass times acceleration, or in units, kilograms times meters per second squared. So drag is the drag coefficient times the air density times the cross-sectional area times the speed squared divided by 2. So our x velocity is the speed times the cosine of our angle with the horizon, as we discussed previously. Our y velocity is the speed times the sine of the angle with the horizon. Our radial velocity is the repulsive force, or the retarding force, the drag, and so because it's opposing us, it's always negative. So the ratio of drag to mass. So we're looking for acceleration, and we have a force, which is kilograms times acceleration. So we're knocking off the kilograms, so we just want the acceleration. Then we have that acceleration. Oh, sorry, that's the acceleration I was looking at. We'll come back to that. So the angular velocity, omega, is our gravitational acceleration divided by our speed. Okay. So now we have our acceleration. And so before, I said that this really is just a component-wise derivative. So if our last one is velocity, then the derivative of that with respect to time is going to be acceleration. So that's what we're computing here. And so our acceleration does not go without bound. Like, there is a terminal velocity, and so the drag takes that into account. So the gravitational acceleration times the cosine of our angle with the horizon. Sorry, times the sine of our angle with the horizon. Okay. And so now we return our derivative. So dx, dy, omega, and acceleration. And I do it like this because I like to think of it like a column vector, as you will if you choose to take ordinary differential equations at a higher level. Okay, so now let's write our integrator. So again, just like before, it's a summation. And so we start at t equals a. So now we're incrementing, we're starting at whatever point our initial value was. We're continuing until we reach our final point, and we're incrementing in steps of dt. And we're using fractions with powers of 2 in the denominator, so we can expect it to actually add up properly when we get here. Okay, so dx dt is actually the result of our sampling function. So as before, our sampling function is the derivative of some higher level function. Okay, and so we pass in our function, or sorry, our vector at time t, so the state of our vector at time t, and then it computes the derivative for us, or the rate of change for a step size. Okay, and then we compute the future state, the next state, term by term. So we have whatever it was, so our 0th component, and then we account for the rate of change at that point in time, and then we multiply it by our step, right? So everything is as it was before. So we have some initial position, we move it forward some unit in time, and then we account for the change in position, so by having that unit in time multiplied by the rate of change at that point in time. So everything is the same as it was in a much simpler time, but the notation has gotten much uglier. But still, it's not unbearable. It takes a little bit of practice, and but it should all look familiar. So this all, when we get to this point, it really doesn't look that bad. The integrator, the only thing different about it is that we're integrating component by component instead of just a single valued function. So vector valued functions really aren't that bad. So this is vector calculus. Probably a little more than you're used to. Okay, so now we have that. We can compute it. And so we can say after time t, or after b minus a units of time, and right now we have it as 1 second, we can write out the position of our cannonball, our 15 kilogram projectile. And then I'm just going to spit out component by component what our vector was at time t. And I could put this in the loop to see how it's evolving. And in fact, I may do that. And then speed. And let's go ahead and put it here so we can track it. Okay, so we have each of our 30, what did we decide on, 32? No, 128 samples written out to the console. And we can see that it never reached the ground. In fact, it's still ascending. So let's space it out a little bit more. Let's give it 10 seconds. Okay, and it hit the ground a long time ago, so 10 seconds was really too much. So let's cut that in half. Okay, so it still hasn't hit the ground at this point, so it took longer than 5 seconds to land. Let's split the difference again, and we'll do 7.5 seconds. Okay, so that was still too long. So let's do halfway between 5 and 7.5. So 6.25. Okay, still hasn't reached the ground, so somewhere between 6.25 and 7.5. So let's do, what is that? That's a difference of 1.25. So we need to add, what, 6.625, I believe. So this will be 875. Okay, so we're below 0. And in fact, from here we can kind of see what time we need. And so it's somewhere between here and here. So let's use that to get a little closer. I'll say 6.25. Almost there. It's still a little too much time. 6:05. Well, you can see that we're going to have to keep cutting in between here. I'll say 6:15, maybe. And we're getting closer and closer to where it was, where it actually hit. And so we can use this to track the amount of time that it spends in the air. Or we could increase the number of samples and then, or decrease our step size, and then use a loop to try and get closer and closer to the exact time, or just have some tolerance of time that we really don't care, we just want it to land in there. Additionally, if we know how long it takes for that event to happen, for it to hit the ground, or we have some other function that tells us how long it took, then we can wait for it to hit the ground, and then we can say, okay, well, where was the x position when that happened? And then we can adjust our launch angle. We can either move it to the upper solution, where we're aiming between 45 degrees and 90 degrees of the horizon on the initial angle, or we could converge to the lower solution and say, okay, well, I want to hone in on that lower angle, and I want it to go, say, 100 meters. So what angle do I need, with this wind resistance and the air density as it is, right, the current air pressure, and at this altitude and so forth. What do I need in order to hit, something that's 100 meters away? What does that angle need to be? And then you can correct. And so, as we were just playing with the time there, right? So the final time, you could see how we just kept splitting the difference. Like if we'd overestimated, then we took something that was between something that fell short, right? And we split the difference again, and we tested to see whether or not we'd overshot our mark and so forth. And so you can do the same thing with launch angle as well. And it should have looked a little bit like a binary search, where we tested, okay, well, I'm at this point now. Is the solution to the left or to the right? And so hopefully, as you're analyzing, what we're doing to get this approach to work, it should seem familiar. It should seem like something that we do whenever we use a binary search. Okay, so I thought this lesson was really cool. It was this introduction to numerical integration. Unfortunately, I've used all of the time we had for a lesson today, so this is going to turn into a bonus lesson. For those of you that are interested, you will have already noticed that this was posted without actually being a formal lecture, and I'll go back and I'll do a lesson on AVL trees exclusively. But I do hope to tie back into this. So, if you're at this point already, then you realize then you've already sat through the lesson. But I will come back to the concept of numerical integration really soon, I hope, so that we can discuss the motion of dynamic systems and how you can use computation to represent something that you would have no hope of doing by pen and paper. Okay, so I'll post the other lecture separately. And for those of you that didn't sit through it, well, you saved a little bit of time, but you missed out on what I thought was a pretty cool lecture. I'll be sure to include the file with the link to this as well, so that you can play around with the different parameters and you can see. And again, I would encourage you to attempt to recreate this on your own. So you have the solution, you can already see it, but go through the motion and try to make sure that you understand what each line actually represents and how it ties into what you're seeing on pen and paper, and then that familiarity of jumping back and forth between code and analytical solutions. So if you see an algorithm or pseudocode in the book, or if you see something that has some mathematical representation, that there is a not so difficult leap into actual code in whatever your language of choice is. And so I want to reinforce that familiarity, and the only way I know how to do that is to encourage you to recreate these projects on your own. So I'm giving you the solution, and even if you want to recreate this one in JavaScript, then I think that would be excellent, so long as you're typing it out and you're not just copying and pasting blindly. Although there is even value to that, because it's still line by line. But try to recreate it, or even better, try to recreate it in a new language. Try to translate it into something new. But I would still feel really good about your efforts, even if you recreated it in the same language, even if you're doing it in JavaScript. Okay, so I will speak to you again really soon with the lecture for today.